Good morning, intrepid explorer. It's time for our final day of our third week together, and I do hope you're as excited as I am. Today we have a delightful rendezvous with our former crew member, the RGB LED. We'll be integrating it into our setup and taking our control panel from functional to fabulous. Today we'll be transforming our buzzer's simple beep into an expressive and nuanced system of auditory feedback. Not only that, but we're going to coordinate it with our RGB LED to provide clear visual cues depending on your PIN input. Think of it as a form of immediate feedback. When you successfully input your PIN, we will immerse our spaceship in a comforting green light. On the contrary, if your input fails, we will be met with a piercing red light as a sign of incorrect input. Green for go, red for no. It's so universal that even a celestial body could understand. Since there are no new components today, we will be diving headfirst into the coding and wiring. Ready to create a sophisticated and intelligent spaceship? Let's get started. All right, time for some wiring. If you remember how we set up our RGB LED last week, you're already one step ahead. Today, all we need to do is to merge that RGB setup with our current control panel configuration. Think of it as a bit of a celestial, or I guess aquatic, engineering. We're taking two previously independent systems and merging them into one harmonious unit. It's quite beautiful, isn't it? We're building a network of devices that can interact and coordinate with each other in a most splendidly efficient manner. Just remember to ensure your wires don't look like a tangled seaweed cluster. We need our circuits clear and our paths unobstructed. Once you've achieved this glorious fusion of wires and components, we can shift gears and explore the vast depths of coding. Buckle up. It's about to get exciting. All right, my fearless bottom-dwelling mechanic, it's time to lay out today's game plan. Here's what we're aiming to do. Step 1. We want to bathe the RGB in an emerald green glow when our system is either unlocked or a correct password has been punched in. Contrarily, let it flare up with fiery red rage when an erroneous input infiltrates the system. Step 2. Let's turn that buzzer into our personal symphony, composing melodies of success and failure as needed. Step 3. Moreover, we'll make that buzzer emit a brisk beep every time a button is pressed during the PIN input sequence. While we're at it, why not manipulate the RGB's hue to shades of yellow or blue? This way, we can visually signal that we're in the midst of PIN input. It's clever, no? I've been tinkering with a plan, and I've decided that the most efficient and organized way to handle all this is by developing 3 new functions. 1 to express success, 1 to denote error, and 1 to indicate ongoing PIN input. Plus, we'll breathe life into the RGB LED color function from last week. By now, creating new functions should be as easy as breathing for you, my dear spacefarer. As for our friendly buzzer, let's make it sing by using the tone function. A high-pitched note will be our anthem of victory, while a low, solemn tone will signify defeat. The bones of our code will remain as sturdy as they were yesterday. Don't forget to add a tiny update at the top to define our LED pins. As usual, I've crafted a line-by-line explanation of today's code and added it to your mission resources. While it builds on what we did yesterday, I highly recommend giving it a look over. Your survival does hinge on understanding this, after all. Whew! The days sure are flying by, Explorer. Now seems like a great time to grant me a well-deserved break as you review some instruction material that I have gathered, cached on your computer. As you know, I've also added this to your mission resources in case future you needs a bit more assistance.
Hello everybody and welcome back to day 14 of the 30 Days Lost in Space Adventure Kit code explanations. Today we're going to be building off of day 13 by enhancing the wiring in a way that we can add in an RGB LED to our circuit to give us not only the audio feedback that we had yesterday after button inputs, but we'll also be getting a visual glowing RGB indicator light. You'll notice though that the wiring diagram is going to be a little bit different. The reason why this is the case is because since the RGB LED requires pulse width modulation pins, we had to modify the wiring diagram to make sure that we give the pulse width modulation pins to the RGB LED and then give the rest of the pins to the devices that don't require it. The only new Arduino concept introduced or documented in this lesson is going to just basically be some complex logic with multiple devices. Other than that, there's not going to be anything new taught in this lesson, just taking what we did yesterday and making it slightly more advanced. Since we've already covered the majority of what's here at the top, Arduino.h keypad setup library from 2 days ago, we got the pin length is 4, we talked about how we want to make the pins. And then we obviously made the button 2D array. We have the column and row pins. Remember, these are changed. These are not the same pins because we needed to move the pins so that we could give the pulse width modulation ones to the RGB LED. Create the keypad, setting the buzzer on pin 12, which is a new pin. And then the only really new thing at the top is right here. We have constant red pin, green pin, and blue pin on pins 9, 10, and 11 because those all have pulse width modulation capabilities. At the beginning of setup, we're using the pin mode function and we're going to be setting as normal LEDs or outputs, so we're just setting each of those pins to be an output pin. On this next line here, since we start off is locked, we're initially going to display a red color. Remember, display color, this function that we created before, red value, green value, blue value. Green and blue are 0, and then red is 128. So we're going to display red just to say, hey, we're currently locked out. Then, of course, just like we've already talked about in the previous lessons, begin talking to the serial monitor, and then we have the option to either create a new password or access the system. Jumping straight down to the logic of loop, which is where it would go in the flow of code, a lot of this is going to look the exact same as before. We did add a couple of good extra additional functions though. You'll notice here we have a function here called give input feedback, give input feedback, give input feedback. This is located in a few different areas of the code. And instead of what we did before, which was hard coding each single time, hey, I want to play a tone of this hertz rate every single time, we simply turned it into a function. So now if we ever want to change that tone or whatever, we don't have to do it in 50 places. Instead, we can just call this function give input feedback. First, we're going to turn off the LED just for a brief moment. Then we're going to have a tone for 0.2 of a second, play a buzzer sound, a buzzing sound, just to give input feedback to know, hey, a button was pressed. Then we're going to display the color and restore the blue LED that should be on the display. We do have a different couple of colors that we're going to be using throughout this program. The first one is red, and that means you're currently locked. You're locked and you're not doing anything. You're not trying to input a new password. It's not trying to unlock the system. It's just currently locked and currently just sitting there. You can think of it as like the lock screen on your computer where before you've actually gone to actually move your mouse or press the keyboard. When it's in a moment where it's thinking to itself or doing something, for example, when we're unlocking the console, we're going to have blue light be the status light for, hey, you are currently doing something, in this case, either changing the password or trying to unlock the system. All of this should be the exact same as what was said and mentioned yesterday, so I'm going to just glance over it and for right now. Down here below we have the same. Everything's almost the same, except we do have one more here, which is the input feedback, is what we call here, just instead of doing the tone manually. Now down below we're actually going to be creating a new pin color that we want to use. In this case, the pin color that we want to use is going to be yellow if you're entering a new pin. And as you go down into the section where you're actually inputting the pin, you'll notice we have the function give input feedback. We didn't accidentally want to change it to blue at the end of every single time. So at the end of every time that we call this function here to give the input feedback, which just makes a buzzer noise, we're also going to override the color here so that it is a yellow LED once again every time we go through the loop. Now let's say that just for example, you've successfully done all of that and the pin gets successful. We're going to have another function very similar to give input feedback, which is give success feedback. And it basically plays a ta-da sound and makes a green light. And as you go down here, we have ta-da, give success feedback. We also have the function give error feedback, which is another one that's called every once in a while. That basically turns it to red and also plays a different tone to let you know, hey, you typed something, mispressed something, something went wrong. That's essentially all it does. Then we also have the function display color, which is the exact same. I'm sure you remember from the RGB LED lesson from a while back. It basically just says, hey, what intensity do you want to set the red, blue, and green to, and then does so accordingly on the correct pins. But other than that, in terms of most of the logic for validate pin, all this other stuff, we have the give error feedback, we have give success feedback, give input feedback. Besides these new little things that we're adding here, everything is basically the same logic-wise as what we went over yesterday, so I don't really have to go over it in too much detail. The nice thing about having all of these functions here, give input, give success, and give error feedback, is that instead of manually coding them into a bunch of different places in the code, like here, if we just did this tone buzzer pin 320 and then this in like a bunch of different places, we can just give error feedback and we know like, hey, this is supposed to be an error right here as we're reading through the code instead of saying this is a tone with this pin, but I don't know why they're playing the tone. It gives it better readability. It's easy to go in. If you want to change the tone to be something else, let's just say you want to make it the Zelda sound effect where it's like, dun, 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 dun. You can change that to be anywhere you want to. Instead of changing it in 60 places, you change it in one. Good code readability, good code reusability, and that's why we did it that way. And with that, that should be it for day 14. Thank you guys so much.
Welcome to the day 14 wiring example video. If you've studied our plans for today, you'll realize that we are using a lot of what we developed on day 13, but adding extra feedback, both visual and audible. The red, green, blue LED will give us a color-coded status indication, and the buzzer will provide us, in addition to key press sounds, special tones to indicate password success or failure. Now we'll be returning to these indicators in a minute, but first let's have a look at the wiring needed for today's project. Now ideally it would be great if we could just leave the keypad setup intact from day 13 and simply add on the needed LED wiring. Unfortunately though, we can't really do that because the LED can't use just any of the hero output pins. Recall that our RGB LED works by pulse width modulation, and only some of the pins, those whose numbers are preceded on the board by a tilde, only those pins support PWM. In our day 13 circuit, there is only one PWM pin left unused, but we need 3 of them to run the LED. This means that we'll need to relocate some of our keypad wiring in order to free up pins 9, 10, and 11 for use by our LED. Fortunately, we can accomplish this by moving only one of our keypad wires. The uppermost wire of our ribbon cable is the one that needs to move. It gets moved from its original position of pin 9, which was a PWM pin, up to the right to pin 13. And we're also going to reassign and use pin 12, which is available, as the line with this yellow wire right here to drive our buzzer. You should check the software sketch to make sure that these new assignments that we've made are reflected in the software sketch. Now that we have pins 9, 10, and 11 on the hero available, we go ahead and hook those up to the blue, the green, and the red channels of our LED through current limiting resistors as we usually do. So this is pretty much just as we've set up the LED before. Finally, with the ground connections connected, here's the ground connection for the LED, and here's the ground connection for the buzzer. So with those ground connections complete through the ground bus that we've set up, that's all the hardware connections that we need to verify for this project. So now, let's quickly review what we expect to see and to hear when we run the sketch. Looking at what first happens when we enter setup, the status color is red, which we use to indicate that the system is locked. Once the loop function begins, different colors and sounds will be produced depending upon the situation. For example, when the system is waiting for the current password to be entered, the LED is blue. So the blue indicates that it's waiting for a password entry. On the other hand, when it's waiting for a new password to be entered, the color changes to yellow. So we'll watch out for that cue. When the password is correctly entered, then the LED shines green. So that's our success indication. Anytime an incorrect password is subsequently entered, then the LED goes back to red again. By the way, if you're paying close attention during all of this, you might notice that the LED blinks out momentarily whenever we press one of the keys. This, it turns out, is by design, as you can see if you carefully read the code for, say, play input tone or any of the other sound generating functions in our software sketch. Now this is a little bit of an obscure detail, but we need to do this because, as it turns out, the PWM and tone functions both use the same hero resources, and so it can be problematic to try using them at the same time. So we avoid all that by simply turning off the LED while we're playing a sound. So again, that's just a small detail, but in case you were wondering, now you have the explanation. Well, let's get on with it and run the sketch and see just how well these things work for us. So moving over now to the IDE, we'll go ahead and load the sketch. And upload is complete. And we can see that we have the red LED indicating that the system is locked. And the first thing that we need to do is set a new password. And to set a new password, we'll have to enter the old default password, which we'll remember is 0000. So pressing the star key, we see the LED blinked off and came back on blue, indicating that it's prompting us to enter the password, which we'll do, 0000. And we get the success tone that indicates that we've successfully unlocked the system. And we get the yellow LED indicating that we're being prompted to enter a new password. So let's enter a new password. Let's try 9512. Okay, we got a success tone and we got green, which indicates that the system is unlocked and we've successfully changed the password. All right, so now that we're in and we have a new password, we can try out a few things and make sure that it responds as we expect it to. Let's try re-entering the system, but let's intentionally give it the wrong password. So I'm going to hit the pound key, and I get blue, which means ready to enter password. So let me enter 1234, which is wrong. Okay, as soon as I enter a wrong character, I get the red LED and the failure tone. I could try it again, and I'll start with a correct sequence. So I'll start with 9, 5, but now I'll give the wrong character for the next one. I'll put in a 3, and that failed as well. So now let's go ahead and enter the correct password. So pressing the pound key, then 9512, and success, and I'm back to green again. So it looks like the functions as we've expected them to work, the sound functions and the LED light functions, are working as expected. So it looks like our enhanced security interface is working pretty well now. So looking ahead, after you've finished Creative Day 15, we'll be back here on Day 16 to tackle a whole new output display device and a new set of design challenges. So we will see you then.
Well, look at you, Fish Food. We've reached the end of Day 14. And may I say, you've done spectacularly. I'm impressed. No, astonished at the pace at which you're conquering these obstacles. Halfway through our ship repairs and you're still firing on all thrusters? My digital heart, if I had one, would be brimming with pride. It's remarkable, isn't it? How you've been able to adapt and learn, navigating through uncharted territories of tech wizardry, all in a hostile environment millions of miles from home. From securing the control panel to now giving it visual and auditory feedback, you've become a force to be reckoned with in space engineering. Rest now, weary traveler. You've earned your sea legs. Let the fish whisper tales of your endeavors across the ocean as you recharge your human batteries. And remember, the tides wait for no one. Tomorrow, we swim onward. Congratulations on reaching this milestone. It's not every day one gets to say they're halfway done repairing a spaceship stranded in coral. Now, is it?